So hello friends, today we are going to discuss about the concept of finding the modulus of the roots of a complex polynomial. Okay, this is a very uh, tough task. Okay, we'll show this using a theorem and then an example. Okay, so we are given a question in this and we'll solve it using, first we'll prove the theorem and then we'll using that theorem we'll solve this question. Okay, so let's see an minus 1 an minus 2 dot a1 a naught whole bar is a decimal representation of a prime number and an greater than 1. Prove that the polynomial px is irreducible. Okay, so let us see the one lemma or one concept to find the modulus of the roots of a complex polynomial. Let us see, we assume alpha to be a 0 of the polynomial px. Okay, then p of alpha equals an alpha power n plus an minus 1 alpha power n minus 1 dot a1 alpha plus a naught, where alpha is a complex root of px. So we have 0 equals p of alpha mod equals mod of an alpha power n plus an minus 1 alpha power n minus 1 dot plus a1 alpha plus a naught. This is greater than equal to a mod an mod alpha power n minus mod of an minus 1 alpha n minus 1 dot a1 alpha plus a naught. Okay, we have used the property that mod of x plus minus y is greater than equal to mod x minus mod y. Okay, this is the property which is. Now again we use another property that mod x plus mod y is always less than or equal to mod x plus mod y, or again I am repeating, mod of x plus y is less than mod x plus mod y, and that we have used to disintegrate these all mods into individual mods. Okay, now next what we have done, we have taken an alpha n common. Okay, here in this step it will be clear, an alpha n common, see, and thus this term becomes 1 and these all terms becomes like this. You can see an alpha n common, this term becomes 1, an minus 1 alpha n minus 1 by an alpha n plus an minus 2 alpha n minus 2 by alpha n an, and so on. Okay, and this again what we do, we take from this 1 minus these terms, we take 1 by alpha n an common and we get alpha n minus 1 an minus 1 plus an minus 2 alpha n minus 2 dot up to a naught. This implies that now this an is greater than 0, alpha n is greater than 0 and 0 is greater than equal to this. So 0 must be greater than equal to 1 minus this term. So so 1 is smaller than equal to this term. Okay, we'll obviously we'll get this result. Okay, if you have any confusion, please write in the comment box. See, we'll get this result because 1 minus 1 by alpha n an when goes to the LHS becomes positive, and 1 remains in the RHS and remains positive, and thus this inequality, from this inequality we get this inequality. Okay, now moving on, see, we assume the maxima of ai's to be m. Okay, where I varies from 0 to n minus 1. Okay, now we have 1 by mod alpha n an m into mod alpha n minus 1 plus mod alpha n minus 2 dot alpha plus 1. How we are getting this? See, 1 by alpha n an, see, 1 by alpha n an. Okay, and this an minus 1 we replace an minus 1 by m, an minus 2 by m, a1 by m, a naught by m, and we get, because all these m's are either equal to or less than m, we get this inequality. Okay, and then this is a GP, yes, with all positive terms. Okay, so this gets converted into this. Okay, this is the GP and this is the sum of the GP. Okay, Now we get the expression this, and three cases would arise for this. One case would be mod alpha is greater than 1, one case will be mod alpha less than 1, and one case will be mod alpha equal to 1. And we prove a particular theorem, a particular concept is valid for all three cases, and we'll be doing so in the next few steps. Okay, so let's begin. Three cases arrived. This, okay. For case 1, what we do, 1 by alpha n m by an, alpha n minus 1 by alpha n minus 1 is greater than equal to 1. Okay, so m into alpha n minus 1 by an alpha n is greater than equal to alpha n minus 1. Okay, and what is this? M by an into 1 minus 1 by alpha n is greater than equal to alpha minus 1. Okay, so m by an is greater than equal to a mod alpha minus 1. Okay, because this is negative, so this inequality obviously holds. Okay, so you get m by n plus 1 is greater than equal to alpha, so alpha is less than equal to m by n plus 1. Okay, moving on, this is n. Okay, moving on, case 2. Case 2, see what was the equation. The equation was 1 by alpha n and m alpha n minus 1 alpha minus 1 greater than equal to 1. And for case 2, alpha is less than 1. So both these terms are negative. So multiplying both by minus 1, both these terms will be positive, and then we multiply 1 minus mod alpha to both the terms, and we get this. We get this. Okay, m by alpha n into 1 minus alpha n is equal to 1 minus mod alpha. Okay, now m by an into 1 minus alpha n is greater than equal to alpha n minus alpha n plus 1. Okay, then m by an is greater than equal to alpha n minus alpha n plus 1 by 1 minus alpha n. Now this is always greater than equal to mod alpha minus 1. So we get the desired result again, that alpha is less than equal to m by mod an plus 1. Now we have to prove that this is always greater than equal to mod alpha minus 1. So let us assume this. For one, the condition is mod alpha is less than 1 greater than 0. Okay, so let us put here this, and we get alpha n minus alpha n plus 1 is greater than equal to alpha minus 1 into 1 minus mod alpha n, because 1 minus mod alpha n is positive as mod alpha is less than 1. So alpha minus 1 into 1 minus alpha mod alpha power n. Okay, gives you multiplying these two terms, it will give you alpha minus mod alpha power n plus 1 minus 1 plus mod alpha n. Okay, alpha n get cancelled out, minus alpha n plus 1 minus alpha n plus 1 get cancelled out. Alpha is greater than equal to 1 is greater than equal to alpha. Okay, so our condition, we are getting this, and from this we can get this. Okay, so we have proved this case also. Now the case 3 is, see what is the case 3. Case 3 is mod alpha equal to 1. Put mod alpha equal to 1 here in this equation. We'll get mn by an. Mod alpha is 1, so mod alpha power n is also 1. So 1 by mod an, m into n is greater than equal to 1. So m by mod an is greater than equal to 1 by n. So m by mod an plus 1 is greater than equal to 1 plus 1 by n. And this is greater than equal to mod alpha. Why? Because mod alpha equal to 1. So 1 plus something is always greater than equal to 1. So this again gets satisfied. This condition is satisfied. All three cases we get the result as m by n plus 1 is greater than equal to mod alpha. So we have arrived at the concept which we make use of in the problem stated earlier. Okay, on the first page. Okay, so let's begin. Now p of x equals an xn plus an minus 1 xn minus 1 plus a1 x plus a0, and an is greater than equal to 2 and 0 is smaller than equal to ai smaller than equal to n for any I except I equal to n. Okay, so p of, now we are given that p of 10 is a prime. P of 10 is a prime because an minus 1, an minus 2, that is a decimal representation of the prime number an minus 1, an minus 2, an minus 3, a1, a0, okay, whole bar. So P10 is a prime, it is a fact, and by we are going to prove this by contradiction that it is irreducible. So first we assume that it is reducible into two factors q and r, okay, where q and r are non-constant polynomials with integer coefficients. Why integer coefficients? Earlier we have discussed that if q and r are if p can be factorized into two polynomials with rational coefficients, then it can also be factorized into two polynomials, non-constant polynomials with integer coefficients. Okay, that was the Gaussian limit. Okay, so p of 10 we can write q10 r10. Okay, then let the zeros of qx be x1 x2 up to xk, and of rx be xk plus 1 xk plus 2 xn. Okay, then we assume now, see, p of 10 is a prime, so prime has only one factor, that is the prime itself and 1. Okay, so so one of these q of 10 and r of 10 modulus has to be 1 and the other one has to be p. So I assume 1 to be 1, q of 10 to be 1, and q of x is x minus x1, x minus x2 up to x minus xk, as you assume here. Okay, and qx can be written like this, where q of x is, here we replace x by 10, x by 10, x dot 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 x by 10. Okay, but we have seen that an is greater than equal to 2 and 0 is smaller than equal to ai is smaller than n. Okay, so ai max equals 9, obviously, but not ai max can be 9, where I varies from 0 to n minus 1. Okay, and an is greater than equal to 2. So each 0 or alpha, each 0, x1, x2, xk, anything that we represent here by alpha, modulus of that root is smaller than equal to 1 plus ai max is 9 by an, and we have to take for proving this, for maximizing this, we'll take ai to be n and an to be 2. So this mod alpha is less than equals to 1 plus 9 by 2. So we have mod alpha is less than equals to 11 by 2. But for all this for all moduluses, for all modulus of the roots, we have mod of the root is more than equals to 5.5. Okay, but 10 minus alpha is greater than, but we have the property again that x minus y is greater than equal to mod x minus mod y. Okay, so 10 minus alpha is greater than equal to mod 10 minus mod alpha is greater than equal to 10 minus 11 by 2, the maximum possible value of alpha, and that is, so 10 is greater than equal to 4.5 for all alpha. So now if 10 minus alpha is always greater than equal to 4.5, then this the q10 equals to 1 will never be possible. Okay, so we arrive at a contradiction, hence the question is proved. So thank you very much. Please do like, share and subscribe my videos for more content like this. Thank you.